Right, so this is a solution presentation for bridging the gap, which appeared in both the 46th and the 47th contest. So in this problem, we have a bridge which can't hold a lot of people, but we have a lot of people, n people, who are trying to cross. And so we have n people trying to cross, and the bridge n could be up to 10,000. And the bridge can hold only up to c people at a time. So maybe there's only 2 people can cross at a time, or 3 people, or something like this. And there's also a torch, or a balloon, or some kind of token, which the people are carrying. And when they travel across the bridge, someone in the group needs to be carrying this token at any time. So you could send, for instance, if c equals 2, you could send these first 2 people over, and they need to carry the balloon. And then one of them could go back carrying the balloon and maybe get another person, and so on. And the goal is to transport all of the people over to the other side. And the different people have different walking speeds. So each person has a walking speed, T1 for the first person, up to Tn for the last person. And when a group of people are traveling together, they only travel as fast as the slowest person in the group. So if these 2 last people, one person takes 1 second to cross, the other takes 10 seconds to cross. When they go together, it will take 10 seconds because the second one was the slowest. So that's the problem. Now you just want to get everyone across as fast as possible. So you want to schedule how to move the people in groups, and making sure that this balloon goes back and forth so that whenever a group is crossing, someone in that group is holding the balloon. So this was one of the hardest problems in the problem sets, both problem sets, and all of the judges who implemented it found it quite tricky to get correct. But ultimately, the implementation is actually not so difficult. So let's see how to solve it. So one first idea that is rather obvious maybe is that whenever you go back, whenever you're sending the balloon back to catch more, to get more people, you should only send one person. Among the people who are still here, there's no point in sending more than one of them back. The only reason to send people back is to transport the balloon back, and you only need one person for that. Then when you're going forward as a group, one observation first is, well, if the number of remaining people here on this side is less than or equal to the capacity of the bridge, you should just send all those people. So that's an easy case. But then the difficult case is, okay, what if there are now more than c people here? Which ones should I send? And you can prove that the correct choice to make is you should send the k slowest people and then the c minus k fastest people over across the bridge. And then the reason that you included these fast people is that you're going to want to use them to go back in trips. So you're going to choose some number k between 0 and up to c, and you're going to send the k slowest people and the c minus k fastest people. And now you have already decided that I'm going to send these c minus k people back. So you already at this point, you pay the budget for, I have now like a budget of c minus k back trips that I can make that I have already paid for. So this leads to a kind of a rather simple dynamic program where we define the cost with parameter r and b to be the minimum cost of sending the r fastest people. Let me correct this. Sending the r fastest people. Assuming we have already paid for a total of b trips backwards because we already sent some fast people over and we paid for their backwards trips already. So the r fastest people. So you can set up this dynamic program, and you can, given a state like this, we have a choice. How many do I send? We have to try all k and try all possibilities. So this leads to a dynamic program with n squared states and n different state transitions, which leads to an O of n to the n cubed running time, which is going to be too slow with 10,000 people. So this is going to be too slow. But there are some optimizations we can do to this to make it fast enough. So the first one is to realize that actually the number of state transition is not actually n, but it's really c, because the choices we have is we have to choose this parameter k, how many of the slowest people versus how many of the fastest people are we actually sending. So it's really c transition. And then the other interesting observation is that this parameter b, how many backwards trips am I paying for? This never needs to be larger than something like n over c, n divided by c, because the total number of trips that we're making back and forth is going to be of the order n divided by c. Maybe plus some small constant, or maybe it's n divided by c minus 1, but on the order n divided by c. So if we do it like this, the number of states becomes n squared divided by c. So now the running time becomes n squared divided by c times c, which is n squared time, which is going in to get you accepted if you implement it. Thank you.